Hey guys, I'm back. So now I'm going to teach you guys a bit about built-in functions. So Matlab has thousands and thousands upon thousands of functions that you can use. They cover everything from basic math operations to specific things about toolboxes, image processing, audio processing, data analysis, so many of them. So in order to get yourself sort of situated in all these different functions, I figured out we just start very basic, very simple, and then work our way up. So if we have, for example, x equals, let's say 16, and I want to use a function on this. There are a bunch of functions that we can use, but as an example, let's say I want to take the square root of this function. So the square root of 16 should be 4, and Matlab does have a function for it, and it's called squirt. So square root, squirt. And it takes in what's called an input. And in this case, the input is just a single scalar value. So in this case, it's just x in our case, and we have 4. Now, you can also have some functions that take in vectors as their inputs. So if x was not 16, x was actually like 9, 36, and something else that's nice square root of 16, I guess. So now if we did square root of x, we had 3, 6, and 4. So the square root operation took in this vector and did square root of 9, square root of 36, square root of 16, as expected. Now there are some functions that can take more than one inputs and have a single output or more than one outputs, but they all basically have the same setup. So they all have a name. So squirt would be the name of the function. In this case, they have what are called arguments. So in this case, the argument here is x, but you can have multiple arguments if needed. And then they give you an output. So in this case, we can say the output is y, for example. So output, function name, and your input, which is your arguments. Now you have some functions that can take in multiple inputs. The easiest one is just to test out is a remainder. So it's this function right here, rem, so remainder, and it takes in 2 inputs. And if, let's see, a good one to test, let's say 5 and 3. So what the remainder function does, it just takes a remainder of 5 divided by 3. So off the top of your head, 5 divided by 3, 3 goes into 5 once, there should be 2 for the remainder, and that's what you end up here. Now, there are some functions that take in any sort of vector matrix input and give you more than one output. And one of them would be this very handy function called size. So if I, for example, made a matrix, and let's say 1, 2, 3, 4, 5, 6, 7, 8, 9. So I have a nice little 3 by 3 matrix. There's a function called size, and size tells you the size of a matrix or a vector. So if I did size of A, it says 3 and 3, meaning there are 3 rows and 3 columns. How do I know this is what size is doing? Well, you can always ask help, so help size. And it says size of something for matrix X returns the number of rows and columns of X as separate output variables. So that's how I know what size does. And naturally, you can always go up here, and if ever there's a built-in function that you don't know what it does, you can just type it in here. So let's say you had no idea how sine worked, you can just type in sine, and then Matlab will tell you about all the functions that are sine related. But that's something that's good to know. Now, if you notice here, you can have multiple outputs. So size of A gives you 3 and 2, but let's say A was 2 rows and 3 columns instead. If I did size of A now, it says 2 and 3. 2 rows, 3 columns. And I can save each of them individually. So I can say row call is equal to size A. And now the first element, number of rows, goes here. Call goes here. You don't have to column, row, and call. So you could have very easily had named it C and D, and that would have been perfectly fine. But because the way this function works and its outputs are the number of rows and number of columns, it's just more handy to give the outputs something that's easily understandable. And that's essentially it for functions. You can have some functions that take in a single input, gives you a single output. You can have functions that take in multiple inputs and give you a single output. And you can also have functions that take in a single input, give you multiple outputs, or vice versa. And I think that does it for how built-in functions work as a base level. So in the next video, I believe we'll go over. See you guys in the next video, and I'll talk to you guys about elementary functions. Bye. Hey guys, so now let's look at some elementary functions that you're going to need in Matlab. So first off, let's talk about the common math operations you're going to be using. So we've already talked about the square root function and also the remainder function, but you can also have, for example, exponentials, logarithms, finding n roots, absolute value, and here are some examples of all of them being used. Now, it's rare for math operations to always just be by themselves. So nobody ever really does a square root function by itself or absolute value by itself or takes the remainder just by itself. Usually math operations happen sequentially or one on top of the other. So an example of that would be this. So if you take a look here, if I want to take the ln of something and then the absolute value, here's the math formula for it, but the equivalent Matlab operation for it is this. So you take the log of it, and then this function is inside of a different function, the absolute value function. So this inner part of the function here will take the logarithm of x, and then whatever this outputs, you just take the absolute value of it. So it's a function inside a function. Similar to how when you do a mathematical operation, you just write the first function you want to do, and outside that, the other function you want to do. Now you might be wondering a little bit about why this ln is here and why we have this log here. If you guys remember back to your Casio or TI calculators, the ln was for logs of base e, and log was usually for logarithms of base 10. Now, because of pure rule of thumb in programming languages, somebody along the line decided that log is always having a base of e, the natural logarithm. So this log is actually an ln for all our purposes. And if you actually want to use log with a base of 10, there's a separate Matlab function called log10 for that. And if you want to use base 2, which is useful for a lot of specific programming applications because computers work in base of 2, then there's a log2 function as well. But there is no such thing as any other log function. So we have log with a base of e, log10 with a base of 10, and log2 with a base of 2, but we don't have, for example, log 4, log 7, log 23. But before I tell you guys how to deal with that, let me just give you some quick little examples of how these are used. So we go back to Matlab here, and I say, for example, log 10 of 10. This will give you 1 because this base is the same as this. But if I do log 100, well, this is the same thing as saying 10 to the second power. This is log 2. If I do 1,000, log 3. Now, if I switch over to log 2, this goes based off powers of 2. So log 2 is 1, 4 is 2, 16, 32, and so forth. Now, if you want to do other kinds of bases, well, you can just do the change of base formula. And change of base formula is very simple. You can do it in any logarithm base you want. So you can do it in the log e, log 2, log 10. And all you have to do is the log of whatever you want. So in this case, log of 33 divided by log of the base that you want. So for example, if you want to do log 4 of 33, you would do log of some base of 33 divided by log of that exact same base of 4. So in this case, log base 4 of 33 could be log 33 divided by log 4, in which case the base you're doing it on is e, but you could easily just do it log 2 of 33 divided by log 2 of 4. It's the exact same, and then you can also do it for log 10. So that's how you can get around that little issue. Now, this is sort of a side issue that mainly it comes about as a programming thing. So in MATLAB, E is reserved for powers. And usually when you're doing mathematical notations, E is the Euler E, the 2.7, so on and so forth. By MATLAB, E is actually something completely different. So the best way I can explain it is just to show it to you. So if you want to do, let's say, e to the first power, as in 2.7, so on and so forth, there's a separate mathematical function dedicated to it. It's called exp. So if I do exp of 1, you have 2.7183 and so on and so forth. If I want to do e to the second power, then I do exponential of 2, and you get this accordingly. So now you might be wondering, okay, if e is for this exponentials, how do I do, for example, 10 to some power or whatever? Well, mainly because you're used to this scientific notation, this is actually how it's done. So if E here is not actually for Euler, it's actually for the scientific notation purpose. So if I type in 5e3, that's not actually saying 5 times e to the third power or anything. That's just saying 5 times 10 to the third power. And this is how you can make really large numbers very compact and easy to do. So I can do, for example, log 10 of, let's say, 1e to the 5th, and I just get 5, because this e stands for 10 to some power. Now, here's a little challenge for you guys. I would suggest you pause the video here and tackle this, and then come back for the solution, which still is on the next slide, but it helps to go through these little problems by yourselves. So what I want you guys to do is make a vector x from -4 to 4, increments of 2. If you don't remember how to do this, go back to the other video I made about vectors and matrices, and then all I want you to do is find a natural logarithm of it, common logarithm with a base of 10, and then the exponential. And then also find the remainder of it using the remainder function, with your second argument being dividing by 3. So go ahead and try that, and then come back. Alright, so I'm hoping you guys did it. So now let's see how you would do this. So I can move this over here. Alright, so let's do a CLC to clean all this up. So first we want to make a little vector that goes from -4 to 4 with a spacing of 2. So open bracket, 2, 4, and we have -4, -2, 0, 2, and 4. Easy. Now if I want to take the natural logarithm of this, that's log, remember, log by itself is always log with a base of e. And I do x, I get all of this as a result, perfectly expected. Now if I do log 10, that's logarithm with base of 10, and you get this, perfectly as expected. Now we also want to do the exponential, so you use the exponential function of x, and you get results. So this would be the same thing as saying e to the -4 power, e to -2 power, e to the 0 power, and so on and so forth. Simple enough. And now the last one we would do is remainder. So remainder of x divided by 3. So this is what happens if you do -4 divided by 3, and that's how much you have a remainder you get. -2 divided by 3, 0 divided by 3, and its remainder, and so on and so forth. Very simple, just a little example problem just to show you how things are done here. So in the next video, I'll tell you guys about rounding functions, which is always useful to have when you're programming. See you guys then. Alright guys, I'm back, and now let's talk a little bit about rounding functions. So in Matlab, there are generally 4 types of functions I use for rounding, and they're listed here in this table. Now rather than just go over and say what these are and then the little example, let's go ahead and just dive right into Matlab, and I can show it to you with some examples. So first off, you have the round function. Now this is one you guys are probably most familiar with. All it does is it rounds towards the nearest integer. So if I do round, let's say 8.4, ask yourself, is 8.4 closer to 8 or is it closer to 9? Well, 8.4 is closer to 8, so this will round down to 8. Now you could also do the other hand, so you do 8.7, is this closer to 8 or is it closer to 9? Closer to 9. So that's essentially all round does. Rounds to the nearest integer, either positive or negative direction. Fix is a bit different. It still rounds to the nearest integer, but fix will round towards 0 specifically. So if I do, let's say fix of 8.4, as we did before, it will round towards 0. So going towards 0 in this direction means it's going to go from 8.4 down to 8. And it's different from round in that even if I do 8.7, it's still going to go towards 0, so it's still going to go down to 8. Now, fix is useful, especially if you go for negative numbers. So fix of, let's say, -2.1. If you want to go towards the 0 direction, -2.1, go towards 0, and that would be -2. Likewise, if I make it an even bigger negative number, it's still going to go towards -2. The idea is it goes always towards 0. Now, the last two are pretty self-explanatory based off their name. They're floor and seal. So floor always goes towards negative infinity. So if I do floor, a -2.6, this is going to round towards the nearest integer towards the negative infinity side. So this will go down to -3. And likewise, if I made this a positive number, 2.6, this will also go towards negative infinity, towards the nearest integer in that respect. So this will go down to -2. Seal is the exact opposite. It just goes towards positive infinity instead. So if I did seal, let's say 3.4, this will go round to the nearest integer towards positive infinity. So this will go all the way to 4. Doesn't matter if it's really small, really small, it'll always go towards 4 because that's the nearest integer towards the positive infinity side. Likewise, if this was negative, this will always go towards the nearest integer positive side. So this will go all the way up to 3. And if I made this even more negative, it will still go towards -3. And that's the gist of the 4 rounding functions you have. I'll see you guys in the next video where I'll talk about discrete math. Alright guys, let's talk about discrete math now. So discrete mathematics deals with a branch of math that is not continuous and usually only refers to math done on integers. So you can do factorization, greatest common denominator, least common denominator, factorials, primes, and such. Now, the best way to explain this is just to go over some of the most used functions for discrete math. These are just a couple of them. There are many more, but for example, you can do factorization, so find prime factors of x. So let's go ahead and test some of these out. So for example, if I do factor, let's say 15, it says 3 and 5. If you remember back in, I don't know, middle school perhaps, when they had you make those little trees that factorize everything, this is exactly that. So if you try to factor, let's say 100, this will break down 100 to all of its little factors. So 2 times 2 times 5 times 5 is 100. They're all primes, so you know it's done correctly. And if you try to factor prime numbers, so let's say like 17, the only factors in 17 are 1 itself. So this is a very useful type of function to have. You also have functions such as factorial. So factorial is that little exclamation point or symbol that you use. So you can do factorial of 5, but you can't do 5 this. You have to do factorial. And all this does is 5 times 4 times 3 times 2 times 1, essentially. Which is the same as if I did 5 times 4 times 3 times 2 times 1. And a lot of times when you're doing mathematical formulas, factorials show up a lot, so it's useful to know that there's a function for it. And you also have things such as rats. Now rats is a very interesting little function that returns back to you whatever number you give it into its input as a fraction. So if I did 0.25, for example, 0.25 is actually 1/4. And that's exactly what rats gives you. It's really useful to have, especially when you're dealing with some decimals that you want to represent more compactly as fractions. And you can also get this to give you very interesting results. So for example, if I did rats of pi, well, obviously pi can't be expressed as a fraction, but the rats function gives it its best shot. And since pi is 355 divided by 113, so let's test that out. And it's pretty close, with some round off. And you can also do rats on other things that are rational. So rats on, let's say, exponential 1. So Euler E is not rational, but the best guess for it is something like this. So it's an interesting little function to know. And you have many other functions as well that you can test out. Primes, and choose K. So the primes will give you all the primes that are less than X. Is prime will tell you for sure if a number is prime or not. And greatest common denominator and least common denominator give you their respective greatest common denominator and least common denominator. So let's go ahead and do a little example here. So use the functions from the previous slide and give me the greatest common denominator and least common multiple of these two numbers, 134 and 12, and then check to see if 134 is prime or not, and if it's not, find prime numbers between 0 and 134. So go ahead and try this. I suggest you pause the video, go back to this little table here, and try to use these functions with these numbers in place. So I'll give you guys a little second to do that. Alright, so assuming you did that, you probably figured it out, and hopefully you did. So let's go ahead and quickly do this. So we want to find the greatest common denominator of, I believe it was 134 and 12. So our greatest common denominator of 134 and 12 is 2. So yeah, if we try to find all the factors of 134 and 12, 2 and 6, 7, if we try to do the same for 12, 2, 2, 3, so the greatest one they both share is 2. That seems right. If we do LCM, so the least common multiple of 134 and 12, looks like it's 804, indeed. Now, the next thing we want to test was prime. So is 134 prime? Clearly, because even it's not prime, but we can still check. Is prime 134? We get logical values, so logicals can be either 1 or 0, 1 for true, 0 for false. In this case, it's 0, meaning this is not a prime number. So we were told that if it's not prime, give me all the primes from 0 to 134. So that's primes of 134, and this will give you all the primes less than 134. So you have 2, 3, 5, 7, so on and so forth. Very simple, just showing you what you can possibly do. So next video, I'll tell you guys about trigonometric functions, which are always nice. Hi guys, welcome back. So now let's talk about trigonometric functions. So as engineers, you're going to get really used to working with trigonometry, sine, cosine, tangents, and stuff like that. So it's good to know that Matlab has a full suite of trigonometric functions that you can use, both the standard and hyperbolic versions. And the one thing I want to express to you guys first is that these functions are always expressed in radians. So they're not degrees like you might be used to, they're always radians. So for example, if I wanted to do the sine of, let's say, 45 degrees as a first pass. Well, you can't just do sine of 45 because Matlab assumes that this is going to be in radians. You're going to have to convert 45 to radians first, because remember, the sine 45 is square root of 2 over 2, so 0.707 something. So clearly this is not that. So remember, you want to convert from radians to degrees, or degrees to radians. You multiply by pi, and then divide by 180. So you should do sine of this instead. So if I did sine of 45 times pi over 180, now we get 0.717, which is close to what we were expecting. Now this can be a bit tedious. So if you want to use degrees specifically, there are Matlab functions dedicated just to the degree version instead. And here's not a full list, but a pretty comprehensive list of most of the trigonometric functions that you'll use. So let's go ahead and try some of these out first. So sine, cosine, tangent, very simple to use. But just to show you guys, if we want to do a sine d of 45, this input expects degrees, so we get the answer that we're expecting. Same thing for cosine of d, just for and tan d as well. This should just be 1, sine over cosine. And if you wanted to, you could also find the inverse. But the inverse is, on your calculators, it looks like the little -1 symbol. So the inverse of sine is a sine. But this expects your answers to, well, the result it gives you is always going to be in radians. If you want it to be in degrees, you have to use the d version instead. So if we did a sine of 0.7071, it says it's this value right here, but we know the inverse sine of this should be 45 degrees. So this is the radians version of that, which is the same one we got up here. And if we did that instead with a sine d, it's saying 44.995, which we know is actually 45 degrees. Round off errors and computational reasons, it gives its best approximation, but we know what it really stands for. And similarly, you could go ahead and test out some of these other functions as well. And if you want to, you can also test out the hyperbolics as well. So go ahead and try and do this little example right here. Find the sine of 30 degrees using the sine function. Use the sine d function to check if you get the same answer. And then use the inverse a sine function to trace results back to the angle that you used. And then answer the question, is this angle in radians or degrees? Make sure you don't mess up between sine and sine d, and the fact that you can deal with both degrees and radians. So go ahead and try this little example out, and I'll see you guys then. Alright, so hopefully you guys did it. Now let's go ahead and test this out. So first things first, we want to do the sine of 30 degrees. So if we want to do sine 30 degrees, we have to convert from degrees to radians. So I would do sine of 30 times pi over 180. And this is 0.5, as we expected. Now we can also use the sine d function instead. Now sine d expects in degrees inputs, so I can just leave it as 30 degrees. Easy enough. Next thing we want to do is the inverse of all of this. So if we did a sine of 0.5, this gives us 0.5236, which is actually the exact same as our input here, but in radians, which is what we expected. If we wanted this to be in degrees, you would just have to do a sine d, and we get 30 degrees. And that was all that was to it. And the answer that we expect for a sine should be in radians, for a sine d should be in degrees. And that was it. So next thing I'm going to tell you guys about is data analysis functions. So look for that in the next video. Alright guys, now let me teach you guys a little bit about data analysis functions. Now, in my opinion, these are the most useful of all of the Matlab functions because of how diversified they are and how useful they are in pretty much any field you're going into. So much so that the functions I'm about to cover right now, some of them I use on almost daily basis, no matter what kind of code I'm writing. So let's go ahead and just talk about some of them. So we have max, we have min, we have the classical mean, median, mode. You can also do sums and products. And then you could also have these sorting functions, and then some of these functions which you might have seen before, such as size, but you also have things like length and null, and then some standard deviation stuff. Now, let's just go through them slowly, and I'll show you how they work. So, first off, we're going to need a nice little vector to work on. So, if I make a vector like this, 1, 5, well, 1, 4, 3, 7, 8, 7, 10, let's say, here's a nice little row vector for us to work on. If I want the max value in this vector, we can visually see it's 10, but the max function will tell us that. Likewise, if we want the min, we can do the min of x, and it tells us it's 1. Now, this function can have either one output or two outputs. You can ask it what the minimum or maximum value is, but also its position in the vector, the index. So you can say m comma I, let's say, and then max of x. And the first value, this m, which I just arbitrarily called it m, this m is actually the value of that's the max. But the second value here, this I arbitrarily called it I, but the second value is the index. So this function is saying the max of this vector x is 10, and it's located at the index position of 6, meaning in the sixth element of this index is the maximum value. 1, 2, 3, 4, 5, 6. Easy enough. Likewise, I can just swap this for min, and it tells me the opposite. The very first element is the min. And a lot of these functions that I'm going to go over have multiple different ways you can write them with options and such. And if you're ever unsure of how to use a function, I recommend you either type in just help and the name of the function, such as help max, and it tells you everything you ever want to know about this function, or go over here and type it in. And this will open up a nice little Matlab documentation window that gives examples and how to do it and miscellaneous things about the function that you might not know about. Always helpful to know. Anyhow, that's max and min. Now let's do the mean, median, mode. So let's make a new vector for us to work on. Let's say 1, 2, 4. If you remember, this notation gives you an equal spacing from 1 to 4, so 1, 2, 3, 4. And then let's do 4, 5, 6. So this gives us a nice little vector that's going from 1 to 4, equally spaced, and then 4, 5, 6. So 1, 2, 3, 4, which represents this, and then 4, 5, 6, which represents this. Now if I did the mean of this value, then it's 3.5714, which, yeah, bears right. And then if I did the median, apparently it's 4. So if you crossed out both here, both here, both here, you end up with the center, which is 4. And if you had an even number of elements here, it would just average between both of them, giving sort of a weighted average, which is how you're supposed to do the median technically. And now the last one is the mode. So this is clearly the 4, which I deliberately put in here. Very simple functions, really. But it's good to know that you can do basic dot analysis using these. You can also use now the sum function. So sum does exactly what you expect it to do. So if I did, for example, 1, 2, 3, 4, and then I did sum of x, so 1 plus 2 plus 3 plus 4 is 10. Easy enough. You can also do product. So product will just do 1 times 2 and so on and so forth. So this times x would be 1 times 2 times 3 times 4. So 4, 8, 12 times 2 is 24 times 1, yeah, exactly that. And then cum sum and cum prod are very similar to the regular function that they're named off of, but they give you each value intermittently. So you can do cum sum of x, and then it'll give you, if x is 1, 2, 3, 4, it'll give you 1, then 1 plus 2, then 1 plus 2 plus 3, then 1 plus 2 plus 3 plus 4. It just shows you all the additions in between. Likewise, if I did prod instead, it will do the same thing, but the product side 1, then 1 times 2, then 1 times 2 times 3, then 1 times 2 times 3 times 4. Simple enough. Now, this is a very interesting function. It's the sort function. So if you had an array of numbers, 1, 5, 3, 2, 4, 10, let's say, and clearly these numbers aren't sorted properly, but you want them to be sorted, you can just type in sort x, and this will sort it in ascending order, 1, 2, 3, 4, 5, 10. Now, if you wanted it to go the other way around, that's called, you would still use this exact same function, but instead, to get it to go 10, 5, 4, 3, 2, 1, you give it an extra argument. And the way you do extra arguments is comma, and then if you press tab on the keyboard, which is right above the caps lock key, it gives you options for things. So by default, it does ascending, but we want descending now. And if we do this, it just reverses the order. Very handy. A lot of functions have extra arguments. If you ever want to know about them, you can just go check the documentation. They'll be more than happy to help you out there. And the next set of functions is a really interesting one. It's the size, length, and null functions. So in order to do those properly, let's say x is 1, 5, 3, 2, 4, 6. Yep. So we now have a nice little matrix to work on. 2 rows, 3 columns. And the size function, you've probably seen it before, it gives you the size of this matrix. So the first element is number of rows, second element is number of columns. 2 rows, 3 columns. Simple enough. And the answer, if you don't specify an output, is a row vector. That just that the first element is number of rows, second element is number of columns. Not that useful by itself. Usually when I'm using size, I save its output to individual variables. So the way I would write this is, because I know the first element it spits out a number of rows, I'll say rows and then columns. And usually it's good to just separate them by comma and then equals. And now rows is 2, columns is 3. There's no real reason why I called it rows and columns beyond just I know through experience that the first element it spits out the number of rows, second element is the number of columns. You could have easily called this A and B, whichever. But that's just how this particular function works. Now, this will tell you the rows and columns of your function, but you can also ask it the length. So the length function gives you the longest dimension of a matrix, regardless of its size. So in this case, the dimensions of this matrix are 2 by 3, so it gives you the longest one. So in this case, 3. However, sometimes you don't want the longest element of the longest dimension of the matrix. Sometimes you just want how many spots instead. That's where null comes in handy. So I'm not interested in how many rows or columns, just how many spots it actually has. And that's what null can give you. Null will give you 6. So if you go ahead and count 1, 2, 3, 4, 5, 6, you have 6 spots. All these little functions by themselves aren't really useful, but you'll see in later modules they become really useful as like a building block for more complicated code. And can't get away from this, so naturally you can do data analysis for mean, median, mode stuff without also having standard deviation and variance. Those also exist. So if you had 1, 5, 3, and I want to figure out what the standard deviation of this is, it's just called std, and the input is just the vector, and it says 2. So average spacing between these 3 numbers is 2. Sounds right. And you can also do the variance, and it says the variance is 4. Very simple, but I don't really find myself using variance or std too much. Now, it's a good thing if I remind you guys something very important about Matlab. Matlab is column dominant, meaning that if there's ever a choice in Matlab for a function to either go on columns first or rows, Matlab will always choose columns. And case in point is just to show it to you. So if you had a vector 1, 4, 2, and then 5, 2, 3, 2 rows, 3 columns. Let's say I want to figure out what the mean of this vector was. That might be a bit strange, so you might want to ask, do you mean the mean of these rows? The mean of these columns? The mean of everything? So there's a bit of ambiguity there. So you can do the mean of x, and because MATLAB is column dominant, it will assume that you mean, okay, what's the mean between these two things, and these two things. And it's easier if I instead switch to something that is easy to understand, so like max. If I do max, then it does the max of these two, the max of these two, and the max of these two. But if I wanted it to do instead the max of this row, and the max of this row instead, I would need to transpose this matrix. And I covered this a little when I was doing my vector matrices video, but all you need to do to transpose a matrix is just use the little transpose single quote tilde symbol, single quote, that symbol that's next to the enter key. It looks like this. So x is this. If I do x transpose, all the rows become columns, all the columns become rows. So 1, 4, 2 was a row, but now it's a column, and 5, 2, 3 was a row, now it's a column. Now if I did max of x transpose, now it's 4 and 5, which is the maximum value in this column and versus this column. Now if I want to do the max element across all of it, then I would have to turn this matrix into just a very single long vector, and there's an easy way to do that. So x is this, but if I said x and then I said, all right, give me x from 1 to the end, so give me every single x value, every single value that's in this variable, it'll just spit out everything that's inside of it. And now if I did, okay, what is the max of this? Now it says 5, as we were expecting. So this is the total maximum value inside this entire matrix. Another way you could have written this is do max of x and then colon. Colon just means everything, and you'll get the same result. So x colon everything will just spit out everything that the matrix has as a very single, very long vector. Useful to know. So take a look at this. And for this example, I want you to use the functions that we were talking about in the previous section, specifically the mean, median, mode, to find it for the matrix x, which is given below, in each column and each row. Then find out the minimum value in the entire matrix and figure out which column does this minimum occur in. So here's the matrix. Find the mean, max, and min for each row and column, and then the minimum overall. So go ahead and take a stab at that, and I suggest you pause the video and go do it. And I'll see you guys in a little bit. All right. So hopefully you guys did it. Let's go ahead and try this out. So first, let's make this little matrix. So it is 23, 34, 17, semicolon to go to a new row, 5, 8, 12, new row, 30, 14, 23, and there you go. Alright, so first, if I want to figure out the mean, median, and mode, I do mean of x, and this will give me per column. Per column. So this is the mean of this column, this column, this column. Likewise, if I did median and mode, it works as expected. Now, if that was per column, if I wanted it per row, remember all you have to do is transpose the matrix. So I can go here and do x transpose, and it does the mean, but now per row instead of per column. So you can see they're different, 19 versus 24. Likewise, I can do the median as well, and the mode. Simple enough. So now comes the sort of challenge of, if I want to find the minimum value in this matrix, I can easily just do, so x, here's the matrix, I can do the minimum of x, but that just gives you the minimum per column. But if I want the overall minimum, then as you saw before, you can do min of the min of x. So this says, okay, the min of x gives you this, but then if I do the minimum on this again, then it gives you 5. And if I want to figure out where this happened, then remember, you can have the outputs m and I that I just arbitrarily made up, and say min xx, and says, okay, the minimum value of this matrix right here is 5, which we already figured out, and it occurs on the first index, which is also true. Now another way you could have done it is min of x, and remember what we did before, this x colon symbol just turns this x matrix into just a very, very long vector. So x just makes a very long vector. Now if I did min of this x, it tells what it is. And likewise, you could have done mi, and this would have said, okay, the minimum value is still 5, but now the index is located at is 2. Why 2? Well, if you do x of everything, it makes a very long vector, and the second element is 5. That's why in the second element here, it's 5. So that's why that's what that says here. But over here, where is it? What we did was we first made the minimum value of x into this vector, and then we did the minimum value of this, and then we asked it for the index, and which in this case was 1. So a slight difference, but same outcome. Just multiple different ways you can get to the same solution, essentially. So that's it for the data analysis functions. In next video, I'll teach you guys about random numbers. Alright guys, now to tell you guys a little bit about random numbers in Matlab. So in Matlab, you can have two kinds of random numbers. You can have uniform random numbers and Gaussian random numbers. In statistics, it's also called normal distribution. So you can have both of these. So let's first cover uniform random numbers. You can use the rand function to create these uniform random numbers, and they'll always start off going from 0 to 1. So the best way I can explain them is just to show you. So you can use the rand function, and it'll give you a random number. And notice how I didn't give an input. Some functions are like this. Rand is one of them. So if I just call it over and over and over again, this gives me a random number every single time. That will always go from 0 to 1. Now, rand can take an inputs of how many random numbers you want to have. So if I said, let's say 4, or 2, let's say, then this will give me a matrix that's 2 rows by 2 columns of random numbers. If I did 3, it'll give me 3 rows and 3 columns, 4 rows, 4 columns. Now if I wanted not a matrix but a vector instead, I can do 1 row, 4 columns, and this gives me a row vector of random numbers. Likewise, if I switch it up, 4 and then 1, 4 rows, 1 column, random numbers from 0 to 1. Simple enough. But often the case is that you don't want to have your random numbers from 0 to 1. Usually you want to have like random numbers from, let's say, I don't know, 0 to 100 instead. So how would you do that? So thankfully, there's a very simple formula you can use. So if you want to generate a row vector that has n uniformly distributed random numbers between 2 given numbers, a and b, and obviously I'm going to assume here that a is less than b, so you want numbers from 1 to 100, not 100 to 1. That just sounds weird. You just use this nice little formula right here. A plus b minus a times rand 1 comma n, where n is how many different numbers you want to have. So if I do, let's say, random numbers from 1 to 10. 1 plus 10 minus 1, so 9. So 10 minus 1 times rand, and let's say 10 random numbers. Or make this a bit smaller, 5. So now we have random numbers distributed from 1 to 10, and to 3.55, 7.3, 5.5, 2.7, simple enough. And if instead you wanted integers, we could couple that with what we learned previously, where instead of having continuous values, you can round up or round down, so the round, floor, seal, and such, and that will give us integers instead. So if I wanted instead to have numbers distributed from, let's say, put this over here, 10 to 20, so I can do 10 plus 20 minus 10 times rand of 1 comma 10, let's say, and this gives you random numbers from 10 to 20. And if I want these as integers, I can just easily use round instead, and then this gives me numbers from 10 to 20. Now oftentimes you probably wonder, are these actually normally distributed or uniformly distributed? There's a handy little Matlab function that you can use to check this, and it's really useful if you want to just test out any data you have. Now this is a sort of jumping the gun here because we haven't gotten to plotting just yet, but if you have data, let's say you have this data right here, so you have 10 to 20 and it's nice and continuous, but you just want to check whether or not this distribution was uniform. You can do what's called histogram. So let me just quickly save this into a nice little variable, x, and the histogram function does just that. It plots a histogram of your data. And if you're ever wondering, well, how does this histogram function work, or does it even exist, just type it into the documentation, hist. You can see there's hist, but they say it's not recommended, use histogram instead. So you can always check the amount of documentation for any and all functions you want to know about. So histogram of x makes a nice little histogram of your data. Now clearly this does not look normally distributed. So the solution for this is just do what they do in stats, just have more data instead. So instead of only 10 units, let's do 1E5. Now remember, E is 10 to them, so it's scientific notation. So what I'm saying here is give me random numbers as a row vector that go, and I want 1 times 10 to the 5th of them. And now if I made a histogram of these, now you can see this is way more normally distributed. If I up this once more, 6, and then plot the histogram again, now this is much more nice and uniform in scale. So it's always good to check your data before you're using it. It's nice to confirm these functions are working properly. And if you noticed, they go from 10 to 20, and it looks like it's nicely uniform. Now the next kind of random numbers is Gaussian random numbers, or normally distributed. Now these also go from 0 to 1, but they follow a normal distribution in what they give you. So generally you're going to get more numbers in that are around the mean, and then as you go out in standard deviations, they get less and less likely. So if you want to use normal numbers, it's very similar. Instead of rand, it's rand n for normally distributed. And they assume you want a mean of 0 and a standard deviation of 1. So let's go ahead and use this. So rand n, and it gives you numbers that have a mean of 0 and they have standard deviation of 1. And likewise, it still accepts in number of rows and columns. So I can do 1 comma 100. It gives me 100 random numbers. Likewise, I can save this and say x is this, and then do a nice little histogram of x. And you can see it sort of looks like that little bell shape that you're used to, but we just need to increase number of random numbers here to really see it. So if I made this 1 times 10 to the 6, now I did a histogram. You can see that this is way more nicely uniform. The mean is 0. It has a standard deviation of 1, following that nice little rule, and it tapers down all the way towards negative and positive infinity. Now, just like in the random numbers, where if you wanted to go between two numbers, we had this little formula. If we want to go between a specific mean and standard deviation, we can use this formula, where we have the mean plus the standard deviation times our function. So if I don't want random numbers from 0 to 1, instead, let's say I want to go 5 plus, I don't know, let's say 2. Let me do a little histogram of this. This gives me a mean of 5 with a standard deviation of 2 instead of 1. Now, I suggest you go ahead and try this little example out. Use rand_n, so normally distributed function, to generate a row vector of 10 random numbers with a Gaussian distribution with a mean of 8 and standard deviation of 1.5. So go ahead and try that. Alright, so hopefully you did try that. And let's do that over here. And it's nearly identical to what we had before here. The only thing that changed is instead of 186, you want 10 of them. And you want a mean of 8. So on our formula, this is m, and this is s, so 1.5. And our x gives us, supposedly, a distribution with a mean of 8 and a standard deviation of 1.5. If we want to check this, we can just make this really large. And now do a histogram of x. And it does, in fact, look like it has a center of a mean of 8. And then 1.5, yeah, looks like standard deviation is about 1.5. So it seems to work properly. And that about does it for this module. So I'll see you guys in the next video. Bye.